Okay, so welcome back. In this video, what we're going to look at is we're going to look at testing a water sample for hardness, and we're going to do that using the EDTA titration. I'll also do a sample exam question at the end. So in our chemistry course, there is an experiment linked with water hardness, and you basically have to test a sample of water for hardness using EDTA. So it's very important to know what EDTA stands for. It stands for ethylene diamine tetraacetic acid. And we basically use a disodium salt of EDTA, as it is more soluble than pure EDTA, and that's very important. That has come up in the past as an exam question. Your indicator in this experiment is called solochrome black. Some of you may have learnt it as aerochrome black tea. Either of these are acceptable in an exam. In this experiment, what you're specifically looking for is you're looking for a colour change from wine red to blue. And that colour change indicates when all of the calcium or magnesium ions have been converted to the EDTA complex. This box down here at the bottom, this is like your little cheat box. This tells you everything that you need to know in this experiment as regards equipment. So in your burette, you'll have your EDTA solution. In your pipette, you'll have a water sample and your buffer. Your indicator is solochrome black or aerochrome black tea, and the endpoint is a red to blue colour change. EDTA in our burette, what it does is it works by wrapping itself around calcium and magnesium ions in water to form a complex ion. So this titration is often called a complexometric titration, as it involves forming a complex. So what you can see here is you can see that the EDTA and the calcium, we can see that the calcium ion gets complexed with the EDTA and we're left with hydrogen ions. The EDTA reagent, it doesn't distinguish between hardness caused by calcium ions or hardness caused by magnesium ions. So because of this, results of this experiment are usually expressed in parts per million, given the shorthand ppm, of insoluble calcium carbonate, as it's easier for comparison. So when you do an exam question on this experiment, you will see the answers always ask you to give your answer in parts per million of insoluble calcium carbonate. The endpoint of this titration is often difficult to detect, so that is why we use a buffer of pH 10 to make the endpoint visible. And a buffer is a solution that keeps the pH constant. So we need to have a constant pH of 10 here in this experiment in order to make the endpoint visible. pH of 10 is used because the reactions between EDTA and magnesium and calcium ions is pH dependent. And also aerochrome black tea, our indicator, requires a pH of 10 to work best. So that's all the theory points for this EDTA experiment. The final thing that we're going to look at now on the next slide is a calculation. So let's complete a sample exam question on this topic. It says, in an experiment to test water for hardness, it was found that 100 centimetre cubed portions of water required an average titration figure of 8.1 centimetres cubed of 0.01 molar EDTA. Calculate the total hardness in moles per litre, grams per litre and parts per million. So let's do part A, where it asks you to calculate the total hardness in moles per litre. So if you remember from our acids and bases volumetric analysis videos, you can solve this using first principles. And the first step is always to do moles per litre multiplied by the titra volume and divide that by 1000. So we know that our moles per litre of EDTA is 0.01, multiplied by the titration volume is 8.10, and divide that by 1000. And when you do that, you get a value of 8.1 by 10 to the minus 5. So step 2 is always to look at your ratio. So we have a 1:1 ratio, so we still have 8.1 by 10 to the minus 5. For the last step, you use your moles from part 3, you multiply by 1000, and you divide again by your titration volume, but this time you divide by the titration volume of the water. So we're going to be dividing by 100. So we get 8.1 by 10 to the minus 5 multiplied by 1000 divided by 100, and we get our answer to be 8.1 by 10 to the minus 4. So that's your answer to part A. So for part B, you're asked to go from moles to grams, and you know that the way to do that is to use your molecular mass. So the first thing you'd have to do here is to calculate the molecular mass of your calcium carbonate, your CaCO3, which is 40 plus 12 plus 16 by 3, and the answer to that is 100. So to go from moles to grams, you multiply by your molecular mass. So you use your answer from part A, 8.1 by 10 to the minus 4, and you multiply by the molecular mass, which is 100, to give you how many grams you have. So you end up with 0.081 grams per litre. For the last part, in part C, we're going from grams to litres to parts per million, and to do that all you need to do is multiply by 1000. So take your answer from part B, which was 0.081 grams per litre, and multiply by 1000, and you get 81 parts per million. So hopefully this gives you confidence in finding the total hardness of water using first principles. If you're unsure, you can go and find a more detailed version of first principles in the videos in the acids and bases section. So that's it for this video. Make sure to have a look at the learning intentions to make sure you understand everything from this video.